Okay. Okay.
You're gonna try to make it a bit larger with the Command Plus. Perfect. Shall we get going?
Yeah.
Awesome. Well, thank you very much. This is our little World Cup special for the Paper Club. If you go to the next slide, please. What's so interesting about soccer analysis, right?
Wait, why does it do that?
Uh,
Oh, I see. I see. Okay.
yeah, no worries. What's the issue with soccer analysis? So soccer analysis, soccer by itself is a fairly physical game, right? And as such, you have people being somewhat skeptical of analysis of that, right? So one of the uh, biggest inventions, I would almost say, of soccer analytics in the last 10 years is the expected goals. Essentially saying for every shot a team makes in the game, what is the chance of that shot leading to a goal? And when you compare teams' expected goals for certain games, you would see that that's even though a team might outperform in terms of expected goals in another team, they might still lose because soccer is inherently a random sport. You could almost see it as like a biased coin being thrown anytime someone shoots at a goal. And there's a significant skepticism still in the soccer or football community about these sort of analytics, at least on the levels of maybe the coaches and the players. So that has been changing a lot. There's this example of some people being quite public about their unhappiness about these metrics, but that these metrics are true is quite clearly be seen by seeing how predictive these metrics are. For example, last night we had Belgium playing Canada, and Canada was outperforming Belgium by a lot. Still, they lost the game, right? So this is a great example of the better team not always winning. If we go to the next bullet point, um, the from the point of view analysis is that not all interesting actions on the field are necessarily on the ball. What does on the ball mean? On the ball is all all these actions where a player interacts with the ball, be it a pass, be it a shot, be it a dribble, a nutmeg, whatever you have. But actually, there is the element of space, like where do players move, and how far are they into the enemy field or the opponent's field, and so on and so forth, which is quite difficult to quantify actually. If you look at a player like Messi, who is arguably one of the best players ever, he's not running faster, um, and when he has a shot, he maybe shoots slightly better, but not by much. But all of his um, yeah strength more or less comes from him being in the right place at the right time. So and that is something that is has not he gets there just before he gets the ball, right? So it's this sort of anticipation of where the action is going to be is actually quite interesting, and if one can get a handle on that, could be really helpful for this sort of analysis, making teams better. And next bullet point, please. And nowadays you have also much more data. So in the past, you would have essentially just have the box scores, team A won versus team B 3-0 or something like that. Nowadays, not only do you have the event data, like player A passed the ball to player B at time X, but rather you have like almost frame by frame data where you know at each point in time there's a player, and from that frame by frame data you can get speeds and all of these sort of things out. So this is a very rich data set that nowadays is available that maybe 5 years ago was just not there.
Arvid, I have a question about this actually.
Yeah, please.
Um, how much how, how much of this type of data is publicly available for like major sports?
Pretty much
Or more
none. I
what?
think publicly available, I don't think there's much data. There are, I think, a couple of samples from So some of the big providers, I think Opta, they have some sample data, like maybe for one season or so out there, but most of the data is unfortunately not publicly available.
Hmm.
You would have to buy it.
But you can buy it, and when you if you are willing to buy it, is there a lot of data available? Like, for example, if I wanted to get the data for this paper from last season to how far back would it go for the Premier League?
Ooh. Oh, I'm not sure. So one of the things is very much dependent on the league, and I think even the stadium, whether the stadium has the ball tracking or player tracking technology in place.
Mm.
Um, I think much of the technology originally comes from basketball, from the States. I think in this particular um, example, they had Premier League, I think 2014, 2015. So it must have been available by then. But generally, I can't tell you what the price is for such data if you try to buy it. I don't know whether it is even like freely available, but I'm sure it wouldn't be cheap. Um, so it's very unfortunate. Yeah. Um, does it answer the question?
Yes.
All right. Shall we go next slide, please? Oh yeah, and actually a lot of new research has been done there. Quite interestingly, I think since 2018 or so, Google DeepMind they seem to have invested quite heavily into this, and they have like a team there, and they really develop um, new concepts, like for example pitch control. Like pitch control is a concept of if I were to drop the ball at this particular point on the pitch right now, which team would likely get the possession of it, which is quite important because it can give you some of the spatial awareness of how the game is being played. Now, next slide, please. Now, what they look at in this particular paper is passing. Passing, of course, is a very important skill in soccer. It's about, if you can go next, well, probably you can just get the bullet points for the whole thing. Of course, passing is important because it means you get the ball closer to the goal. And of course, the closer to the goal is, generally the higher the chance of a score being made is. Um, Now, big part of that paper is that not every pass is just as likely to succeed. Um, the position of the opponent team is quite important, as the speed at which players are moving at any point in time is important, whether a pass is likely going to be made it or not. You can also imagine that not all passes are equally valuable. If I bring a pass with very high accuracy right in front of the opponent's goal, there's a much higher chance of it being you know translated into a goal than if I have a lot of backward passes that are just going back and forth but don't add anything to the game. And so any meaningful analysis probably will take that into account. Um, there is the effect that players do choose which pass to attempt, right? So at any point when a player makes a pass, he chooses essentially from his teammates where he could have made a pass out. And the question is, can one use artificial intelligence to understand passing in the sense of um, where is the most value generated? How likely is a pass to succeed? Especially, can a player improve his passing ability by making smarter choices effectively? Right, next slide, please. Yeah, I think we can also go through here. So the one of the contributions that they claim to generated pass success probability surveys for the whole pitch, aka if I'm a player standing here and I make a pass to any other point, is the pass likely to be successful or not? um, one of the other uh, key results is that they essentially generated or created a architecture that allows to ingest spatial temporal data, especially soccer data, which is quite exciting. There are quite a few practical applications of this. For example, to calculate what is uh, the chance a particular player takes a pass, and of course, it's also important for the other team is like to anticipate where would a pass likely to go, because then like games theoretically they can move and try to optimize their chances based on that information. And what is actually also quite important in this field is that the results should be visual, meaning that you can talk to people that are not technical at all, that are, soccer players, which, without being mean, tend to be not the brightest people. Um, you still want to be able to tell them what it's about, and help them make better choices. And next slide, please. So what do they have here? So they have tracking data for each player, sampled at 10 hertz. So every tenth of a second, there is a point on an L by H grid. It says a player was there. And the passes are essentially event data, so they are tagged manually. And at every point in the game, there are several layers of information available. Here, they take the variable C. We're going to talk about what C is in practice, but this is then information about distance of the ball to any other place, and which is also again spatial, um, speed of players, and so on and so forth. So it's potentially, I think in practice it was C equals 13, so quite a bit of extra information on top of just where the players are. It's quite important to know that the information about is not just important of where the ball is right now, but also spatial regions quite far away from the ball are important, in order to make these pass selections. And the target is to find, um, yeah, again, whether a pass would be successful or not, given we would, um, or we would try to pass from the current position to that point. Okay. Next slide, please. So they define the soccer map, which essentially is uh, your input soccer field, the pitch, plus its C dimension into a number between 0 and 1, essentially telling you what's the chance of success. I don't know why they call it its own name. It's yeah, seems to be a bit big, but it doesn't have to be normalized though. That it's normalized, of course, at each. It's not it is a number. There is a probability at each point, but of course over the whole pitch it is not normalized. That is maybe something to keep in mind. And next slide, please.
Why do you think they did it that way?
It's just how the data is available. Right? If you look at what they actually end up doing is they take their passes and sort of take snapshots for the game data at each pass, and then when you do it like this and you try to train it, this success chance is the easiest thing to actually build around, just because you know where the ball ends up going to. There's always the fact that the players choose where they pass to, and that is, I think, one of the weaknesses here, that they don't really address that much, that there's a selection bias of what works and what doesn't.
Mm.
Yep.
Yeah, I was just thinking that it feels kind of weird to me because, like, as you said, a pass goes to a specific part of the pitch. So, for example, you'd expect that all of the logits or all of the probabilities that are not on the path of the pass would be zero, no? Or yes?
You would think so. It's like what a bit of a question is what is a successful pass? You could always argue that a pass that goes somewhere where there's no player can never be successful, because I think almost by definition that the pass has to be interceptable by a player from your team. So I think you could implicitly just set everywhere that is outside of a certain radius of each player to zero, because just there's no chance of the ball getting a player getting to the ball position if the ball would drop there. Um, they don't do that explicitly here, but I think by training the way they do, they sort of get these pass probabilities implicitly, just because, yeah, if you train, you always, if a pass is successful, clearly that the pass goes where there's a player, and so by this implicit data relation, I think that the model learns that the pass
Mm.
come close to players.
Okay.
Yep. Next slide, please. Yeah, so here that is the target location loss. So that is the log loss they define for their problem. Essentially, if the loss is evaluated at the point where the pass went to. So again, here's where the selection bias comes in, right? So you don't evaluate the loss at any points that has not been selected. And again, it checks whether the pass was successful or not. And then it's just a standard log loss of that point. And that is the thing that generates your 2D map. Again, it's not really randomly selected the points, but I think it is fair to say that any point where you don't shoot to that is outside a certain player radius, it should be essentially 0 anyways. So it's again it's a bit of a definition. What is a successful pass? Remember that there are some Google DeepMind papers, I think, where they get actually quite smart about like when is the team in control of the ball? Do they just because a player touches the ball doesn't mean that he's necessarily in control. So I think then they would count like how close is the ball to a player for a particular period of time and so on. It can get quite sophisticated there. Cool. Any other questions at this point? Then next slide, please. So how does the actual data look like? So they have several matrices that they group into four selections. One is, if you go to the next bullet point, is the position of each player and the velocity of each player. So that is at the time of the pass, right? Or just prior to the pass. So even though we have our 10 hertz sampling rate, much of the data is essentially collapsed out into just the point in time before, and using the player velocity and the player positions essentially. Now in practice, that is actually also quite tricky because much of this data is not always perfect. So if you do calculations of velocity, sometimes you get anomalous results, like say a player is behind a camera, is where the camera is not seeing him, or so. That if you look at the velocity just by looking at the player coordinates, you would think they're superhuman, but in reality they're typically not. So in practice, one has to do quite a bit of, I think, feature engineering to normalize that. At the same time, they add then the data for the defending players, again, same players. Now, these are all sparse matrices, right? On your L by H matrix, there are only 11 players at any point in time per team. So most of them are 0, but they are multidimensional as well, right? So you have the velocities are 2 numbers, and the positions, the velocities have a dimension to them, essentially. Then the next.
I have a question. So is the data just as vector fields basically?
Yes, I think they are 2D matrices, and for the velocities, I think the entrances are like, for example, the x coordinate of the velocity, and then on the second matrix, the y coordinate of the velocity.
Yeah.
Yeah. Then the next one, the next group of features are the ball positions. Essentially, the distance of the ball to the goal and the distance of the ball to each point in that space, right? So if you know where the ball is and you have this 2D field, then you know also where each XY coordinate, essentially how far away from the ball that is in that particular point. And it's also encoded as an angle, which if you look for the next point, I think the goal point, they also tend to use angular coordinates. That makes sense because if historical data shows that if you look at XG, so expected goals, typically it's the distance to the goal and the angle to the goal that are like the main factors to determine whether a shot on goal is going to be successful or not. Naturally, if you are just in front of the goal, so you have a large angle to the goal, there's a much higher chance than than if you are like shooting from the side in a very funny angle, and also the distance to the goal, right? So if you're very close, much more likely to shoot. And they sort of use this notion and encode it in these matrices. Okay, and next point, please. Yeah, there's the goal positions, and then next, please. Yeah, they use sines and cosines. Just to get the relative angles of the players to each other. And so the pixel size is roughly a square meter. So this is quite fine grained on your soccer pitch, which is quite cool. Okay. Next slide, please. So this is what the architecture looks like. So I can't really point with my mouse, but what you see is that you have your original map size, which is your 104 by 68 by 13, and it sort of gets split out in the first step into 3 components. Essentially, one being the original size, which is like the very bottom path. One is the middle path, which is like essentially downsampled to half the dimension, and then one that is downsampled even further to like a quarter of the original resolution. And this is done so that the fields that are being generated can see different sizes of or different spatial scales of the soccer pitch. And each of them, they call it a prediction layer, which is essentially just the value to make it one-dimensional, and then they fuse them together by using one-by-one convolution. So it's a very almost a fairly simple kind of situation. And the big step really is that you split down your dimensions, downsample, do some processing, and then fuse them together, and at the very end have a sigmoid activation, and then you choose the pixel you want to evaluate. It's not much more complicated than that. It looks, I think, much more complicated than it actually is. Okay. If you go to the next slide, we have some details about the individual steps. So yeah, we have the convolution at the different spatial scales, just to for the model to get a different feel for the different dimensions on the pitch. The upsampling is done non-linearly, so it's a convolution layer with then I think a dense neural network with a convolution layer afterwards. Yeah. Next step, please. The prediction layer, I don't really know why it's called prediction layer, because they're linear activations. I don't know what is being predicted here, but essentially it I think makes the channels one-dimensional again in their numbers. I think that's all that's happening here, but it seems to improve stuff. So that's why it's good. Next step, please. Yeah, the diffusion layers, they're quite cool. Essentially, you have a one-by-one convolution, but you mix essentially the different channels of the different layers. So the upsampled layers that come from the very rough features are sort of superimposed with the fine-grained features you have on the other layers, and it's essentially being trained of how much each of these layers are weighted against each other. So that is quite efficient. The next step, please. Yeah, and then sigmoid activation for the final prediction is standard, really. And next slide, please. Oh yeah, sorry. Yeah, there is, in my opinion, a bit of a bias, because it's not a random pass, and even among the different players, there's probably in different game situations, you would not expect that each player is being equally likely to be shot to, right? So very rarely will players pass to the goalkeeper, and so whether that means that a shot to a goalkeeper would not be successful is another question, really. But it's probably just a limitation of the method, really. Next slide, please. So what is the data set? So we have these 740 Premier League matches sampled at 10 hertz, about 350,000 successful passes out of and almost 90,000 missed passes. So it's generally quite a high success rate. They split the data 60-20-20, which seems quite generous actually in their validation set. And but they stratify on the success rate. And yeah, next slide, please.
I have a question.
Yeah, please.
Do you know if they saw anything interesting in the downsampled encoded field?
I didn't read on any of that. I don't think they looked actually at the activations of each layer. Would be probably quite interesting.
Yeah, it would be. Yeah. Okay.
Cool. Next slide, please. Yeah, they optimized using Atom Optimizer, trying different batch sizes and the parameters of that optimizer. And to benchmark, they actually use two other models, LogisticNet and Dense2Net. I don't know the exact details of those, but they help these models by actually handcrafting features that one knows are quite helpful, such as distance of the path. So if I were to shoot to that guy, how far away is the path? Right, so you could expect that further passes are not are less likely to succeed. And and they also handcrafted features of how crowded is the target position. Are there many other players around from the opponent's team, because that again would make the pass less likely to succeed. Go to the next slide.
Two things here. One, I felt like their big claim was that they're not using handcrafted features, but I do feel like some of the feature maps that they calculate are heuristics. You know,
Yeah, so
it's not like they're taking completely raw tracking data and feeding it into the model. So I was like, I mean, you're using less here handcrafted features, but it's not that you're using none.
Yeah, I would agree. Like the feature maps at the beginning, like the angles and distances of the goals, the target, and so is a form of feature crafting. I totally agree. It's yeah, just because they know it works. But again, they don't take, for example, the pass distance itself as a feature. So well, actually they do, right? Because they have a goal map that checks for the distance to the ball at each point in space. So you could, yeah, you're probably right. They they do craft quite a few features implicitly.
And then the other thing is just, I was surprised that there was like, it seems like these baselines were completely fabricated just because there was no citation for either of them in the paper.
Yeah. Yeah, probably there is not that much literature actually out there for these. So
Okay,
I think
makes sense.
they because they are the only ones who sort of attempt this problem, that's why they use these benchmark models which solve similar problems to benchmark, essentially just showing that their SoccerMap architecture is superior to those. One of the things that I quite like is, yeah.
Sorry, I had a question. What do the handcrafted features actually? What are they used for? Like, why do they have to do these sort of handcrafted features?
I think to make the logistic net better, right? So the values the models they use there are quite simplistic, and it's kind of unfair, right? As Peter said, in the original data maps they actually input, they do give quite a bit of information about the ball position and the distance, especially the distance of the ball to the potential passing point. And I probably just to get like some level playing field, they handcraft these features for the benchmark sets as well, so that they can have some fair comparison, really. Like I said, I don't know exactly how LogisticNet and Dense2Net look like. What exactly is the data input? Yeah. LogisticNet might not even be a spatial thing. I think you might just give it the path coordinates and how crowded it is, and then have a logistic regression essentially on saying how likely the pass is to succeed. I'm not sure. Yep.
Arvid, I had a question.
Please.
What generally confused me from this paper is that when they compare the architectures, they claim they have more than 1,000 times parameters than LogisticNet, but their inference time like barely goes up. You think this is in table 1, but the way they sort of how would you say justified is that they got a good ECE, which I think it's the what compares their accuracy with the confidence. So now I'm thinking it's probably not worth asking. I should actually go and check with those specific papers how their architectures differ, because at this point I'm not sure what they're doing to their architectures that the inference time is barely changing, but the parameters are times 1,000.
Yeah, it's a bit of the thing, right? What does inference time mean, right? So it depends very much on your CPU architecture or GPU architecture as well. That seems to be it's I think just a dense neural network with a logistic output. That's why later on they show it has much less parameters. That the number of parameters is not proportional to the inference time is I think to be expected.
Yeah.
Later when we get to that, I think the important bit is that the inference time is still faster than the sampling rate, so that in principle you could evaluate it, I think, in running, which could be quite attractive for certain applications. Of course, you would still have to smooth a lot of stuff and so, but could be interesting during training or so. That I don't know, with augmented reality or so, that you could actually, in principle at least, have players as they run, tell them, like, give them a map of where their pass is likely to succeed, and therefore train them maybe to be better at pass selecting. That could be one application. So that's where this inference time is potentially useful. But I don't think one should take the optimization for inference time as a useful measure of anything, really. It's more saying that, yeah, it's fast. That's good enough.
That actually makes sense, because in most computer vision applications, you're kind of worried about weather condition, external sources like obstacles. But in most sports matches, they have measures that can deal with those. So your only inhibiting factor would be your model should be able to run real time. So I can think it can relate why they're stressing on that more.
Yeah, potentially. Again, it's more like how these used in practice, and I think, I mean, if you look at the authors, I think one of them is working for I think both of them are working for Barcelona. I think the other one might be Liverpool. So Barcelona and Liverpool are the two teams that I think make right now them and I think Munich are the ones that will make the most of these sort of novel analytics, and they might have the technical know-how of implementing them into their training. Yeah.
True. Cheers.
Anyways, next slide, please. Yeah. So here's the calibration metrics. The expected calibration error is, I think, as we know it, you essentially cut your predictions into the small bins of what your model thinks is the probability of the pass succeeding, and then you check against the actual outcome and see whether it is in the same range or not. And if so, are you constantly under or over predicting in those bins? It can be quite helpful because if you're significantly out, you know that your model might have weaknesses that you can calibrate against to improve your model. Of course, that means that you have to. This is maybe why the validation set is so large, because you have to use a sort of data set that is not used for training in order to get these sort of predictions out. Go to the next slide, please. Yeah, results. So that is the calibration map. The comparison of the three models. we see that the inference time is, as you mentioned earlier, is not drastically bigger, even though the model itself uses a lot more parameters. Of course, that is because it uses GPU acceleration and all of these sort of things. That so it just means that the number of parameters and the inference time are weakly correlated across these samples. We see that the logistic net has the best calibration error, but has significantly higher log loss. So meaning that the model is more uncertain most of the time. So which probably is the thing that gives it the higher log loss, but it sort of is correct about being uncertain in the sense that where it is uncertain, where it says the chance is 50-50, it is really a 50-50 chance. If you look at the fraction, ideally, right, we would expect a straight line. And for the logistic net and for the SoccerMap, we do see it roughly. Now, interesting enough, just by looking at it, you'd think that the SoccerMap probably would be the better in terms of expected calibration error. There's only, I think, at one bucket at 0.75 or so, where there seems to be quite a significant difference between the expected chance of success and the observed chance of success. But of course, it means also that the data points are not equally distributed across these bins. There is, if you look at XGs, so they tend to be clustered typically across lower values. So there's a very good chance that also these pass probabilities are not evenly distributed between 0 and 100%, but rather somewhere in the middle. And that might be why even a single bad bin can give you a higher expected calibration error than for the alternative model. This is just a guess. I don't know the actual numbers. And next slide, please. So this is where it gets really interesting. So this is if you calculate, or if you evaluate the probability of success at each point in space. Now this is a bit weird, right? So here's where the model is perhaps a bit odd. So first of all, where's the ball, right? This is white dot above the middle to the right. Can you see it? I can't really point. Yeah, there it is. Now one of the things one sees is that the probabilities are asymmetric with the velocity, right? So if you look at the player to the top right from the ball position, he's of the same team, so potential target. You see that the probability of a successful pass in front of the player is much higher than behind of the player. That takes into account clearly that the player is moving into that direction rather than the opposite direction, which probably would flip the probabilities. now when we see these numbers, it has like red quite high a lot of places where there is no player, which makes me think that one can probably improve upon this by saying that where there is no player, there's just simply no chance of a successful pass. Here it's not done. So I don't know what actually the pass success probability means here far away from a player. Would that be the same as the chance of someone of the same or the different team taking over the ball? I don't know. So yeah, the interpretation of these values is not quite straightforward. But again, the important thing here is close to the players, we see the values are high. The values are very low for very close to the opposing players, and they take the velocity of the players into account. And sorry, but perhaps this is also visible is that a player, say in the top right, who seems to have a higher velocity, also has a higher region of where the pass would be successful. Essentially meaning that if a player has more speed, the effective space in which he could accept the pass grows larger, as probably would make sense, rather than if a player would have to accelerate first to get to a ball. And next slide, please. So here they do an ablation study where they turn on and off the different sampling, the different layers. Interestingly enough, they found one version, I think, without the upsampling that was better in terms of log loss, but it would create visual artifacts that were not really helpful, and that is of course important when you want to share your results with non-technical people. That's those are the kind of things they notice immediately, and you would get flag for that, and so that's why they take the model that is not the best, but has the best practical properties, which makes sense. One thing that is I found a bit funny is that if you look at the NF column, which is the number of sampling nonlinear sampling layers, I think, if they are always at 2 except for the very last step, they have the value of 4, and the value of 4 was decreasing log loss. So of course it begs the question, what would happen if we take the best model and also increase the number of sampling layers there, whether that would help, or whether that is something that or it might be though that this is something that has to do with the architecture, that this only makes sense in these low level sampling in these D8 sampling layers. I'm not quite sure about that. Next slide, yeah. So there are some other applications. So what if you replace so if you take your trained model and replace the sigmoid with the softmax, they claim you get path selection. I don't think that is quite true, because as we saw in the previous picture, right, we got significant probability in places sorry, where there is no player, and so I don't know whether this actually would be really a path selection. I would almost think this would be a separate model that has to be trained based on this path targets in your data set. Another thing that one could do is, rather than training whether a path is successful or not, weight by how is the XG of the path position. If you remember, XG was the expected goal rate if one were to shoot from that position. So a path that goes to a place that has a high value should almost be more valuable, right? Even though if the chance of the path being successful might be slightly lower, if the path is likely to result in a goal, such a path would be considered valuable, and probably one would have a better model than or more useful model than what is there. Now we go to the next slide. So they did that here. On the left is the path selection probability, and I don't know what they did there, whether they here the probability seemed to be so that very far away from the players it is essentially 0. I don't know whether that is yeah, the normalization didn't look like it in the previous pictures, but I don't know whether they added additional down weighting away from the players or so. It might be just a trick of the eyes as well. And on the right hand side is the path value, where one sees that closer to the enemy goal, opponent goal, the value should be in principle higher. It's hard to see. You would also expect I don't actually know whether that really makes sense, because the say if the ball gets intercepted by the opponent's team, and the opponent team is in a state where they could score a goal very easily, then the negative value should also go down further. So you would expect that the red goes brighter towards the right and the blue goes brighter towards the left. I don't know whether that is something we can see here clearly or not. Yeah, that's that. If next slide, please. Yeah, that is actually quite an interesting application. Optimal passing. So at each point, a player who actually passes the ball has several options of attempting the pass, and we can now check. Say each player has like essentially can pass to any of their 10 teammates in a particular radius of those teammates, where is the best point to pass to. And then we could check whether that player actually passed that there, or did he choose a different player that has a lower chance of success. And at the same time, there's on the right hand side, how would players have to be moved within limits? So say we could move at each point each player by a little bit. How would each player have to move in order to optimize the chance of a pass success? That's quite interesting, right? Because it can tell a team how to arrange themselves, and that is, of course, for a soccer team very, very valuable to know that if a player has a certain chance to be always slightly off point, if the coach can correct for that, that can make the team a lot more successful in successful passes, and then also, of course, high value passes. Next slide, please. So they add a new metric that essentially measures how good is a player compared, or how good is a choice of pass a player tends to take. And it's they call it the pass completion added. So how much does the player add to the pass choice? And if you look at the metric, so it essentially is the sum over the successful passes and the misses. And if you go to the next bullet point, the successful passes count more when the shot was a bit difficult, right? So this is the 1 minus y hat square. So y hat is the probability of the best pass. If the probability of the best pass is 1%, so this is very, very hard to make that pass. If the pass is successful, the player gets more value. Makes sense. It's a says something about the quality of the player, but it also penalizes if the shot taken was not the best possible shot. And at the same time, the misses, if only count when the player chooses a path that was not optimal. And so the PPA gets lowered if the player is bad at decision making. And if you go to the next slide, we can compare. It doesn't count for the value of the pass there. That's fine. If we look here for the top players according to the PPA per 90 minutes, you see most of them are very well-known players like Özil or Eden Hazard, who are known to be very creative midfielders. And if you look at their prices, player prices, they also do have quite high player prices. So one would think that this PPA metric actually tells something about a player that maybe in previous analysis was missing. So if I were to say I'm a football team, I don't have much of a budget, I'm a maybe lower league team, I could use this metric to find out players of lower leagues that have a high PPA value that maybe other teams are missing. So I might be able to buy a player for low value that actually is better than I would expect. And that actually is what happens, right? So the say Brighton Football Club, they made it into Premier League essentially by being very, very smart about buying players cheap and then playing them and then selling the players as well, because of course once a player are successful in a particular league, their value goes. And this is one way for a smart club to actually make additional money by identifying playing talent that is undervalued, playing them for their benefit, and then selling them again when they might be overvalued. Next slide, please. Yeah, that is also quite interesting that different teams would have. So if we were to train the data on different teams, you see that different teams have different preferences. I think on the left we have Liverpool, and on the right side Burnley. Liverpool, a fairly strong team. You see that the short pass has a higher value, whereas Burnley, which was a worse team, they try to make more long shots because they know that they can't. They probably have a weaker ball control, so the way for them to make potential goal shots is to give long passes and that players shoot them. And so you can tell from the map where a team is likely to shoot. Of course, if you know that for your opponent team, you can before the game, talk to your players about that, and there's a chance that you can find a strategy that counters that. So that there is a value in having this kind of intelligence prior to a match. Okay, next slide, please. Yeah, so this summary. SoccerMap is a fairly new approach in how to use data that maybe was not available many years ago. So it's a new data that is being used in a smart way. Next bullet point. Forgot what I think the main feature is that you have these different spatial hierarchies that get spread out, but then also combined again, and that captures something about the passing problem that otherwise it wouldn't. It is quite adaptable to different use cases. Just by changing the loss function, you could get several applications that seem to be useful in practice that make soccer analysis or football analysis quite useful for the coaches. And next bullet point, I think the big point is also that it's very visual, right? You can show people those maps, and they will intuitively understand what it is about. So you don't have to have a degree in that, and that makes it very practical in real life applications, aka at the club level, preparing, coaching the players. Yeah, that's it. Thank you very much.
Thanks, Arvid. Yeah, it was. I really like this paper. I actually kind of felt like it was maybe the first draft of something that might become highly used. But in relation to that point you made about Brighton, I was thinking also that probably if you're in a lower league, you probably can't get data on players.
Yes. Oh, well, it depends, right? So championship also, because you often play in the same stadium as the big ones. As long as the tracking technology is in there, you can get it. It's more than for international players. Finding international players in countries like somewhere in Africa, so it's a lot harder, I think, to get reliable data. Like, for example, right now Saudi Arabia, right? It's very hard to judge whether Saudi Arabian players are any good or not. Clearly, Argentina, but it's very hard to judge beforehand, right? Yeah.
I have a related question. Would it be possible to run similar models based on camera videos, not the fancy high frequency ones or the radars they use on stadiums, but a normal camera?
Like a camera on your phone.
No, like a broadcast camera. So not training not from training games, but from lower leagues, which still have cameras, which still broadcast.
Yeah, there are definitely teams or like companies that try to do that try to extract player positions using camera data. I think there's a group in Canada that does it. It is probably less reliable. Say sometimes a player is hidden. Sometimes the camera moves away and so on. And it can be quite tricky actually to get this continuity, like which player. Say if a player moves, is it still the same player or is it another player that just looks very similar?
Yeah, and if it's a corner kick, it all gets very messy, right?
Yes. Oh yeah, exactly. And
yeah.
So it is possible, but with limitations, of course.
Because for games like baseball or even basketball, these things have been done, but maybe mostly with manually collected data. And in baseball, you don't need to track the players; you just know who hits which base.
But baseball, you have other technology. It's called Hawkeye. Essentially, you have
it's a radar, right?
I think so. I don't know. I think it has also a visual component, but
Okay.
they are quite smart, right, about getting like spin of ball and so as well, which is quite valuable to analyze whether a pitcher is very particular in what he's doing.
Nice.
Cool.
Great.
No more questions?
Yeah, that's what I was going to ask as well. If there's no more questions, thanks Arvid for this paper. It's nice to see a practical paper that has like some really interesting and valuable use cases in it, instead of just a lot of times we see a lot of papers that are benchmarking against other papers on publicly available data sets. So really cool.
Thank you.
Yeah. And
Yeah, thanks, Arvid. Very good paper.
thanks everyone
you.
for coming, and hopefully you all have a good weekend. And happy Thanksgiving to anyone who.
Peter, before we end, I want to make a quick announcement. In 2 weeks, we'll do a paper club in the evening at 6 p.m. At a company called Data Spartan. Their offices is near Moorgate. I updated the meetup. I'll send a message around also there. But I would appreciate an RSVP so we can tell them like how many people are coming, how much lunch or dinner to prepare, and then will be a nice event, I hope. Yep.
Excellent.
Thanks all.
Thank you.
Thank you, everyone. Bye-bye.